A 150-pound man is hanging in midair on a stage, held up by nothing more than a single drop of superglue, smaller than a teardrop. No cables, no hooks, just one tiny drop of glue supporting his entire body weight, while millions of Americans watch it happen live on television. What almost no one knows is that the very glue holding a man in the air had been thrown away twice by the man who invented it. So how can such a tiny drop of glue be so incredibly strong? Welcome to Mido Discovery, where the most familiar why questions often have the most surprising answers. That tiny liquid is scientifically known as cyanoacrylate. It was first created in the United States in 1942, completely by accident inside a military research laboratory. And from the very beginning, it was dismissed as a failure and thrown aside. Today, it can be found in almost every home under a much more familiar name: superglue. Unlike ordinary glues that can take hours to dry, cyanoacrylate needs only a few seconds of contact with the tiny amount of moisture naturally present on almost every surface to create an incredibly strong bond. But behind that remarkable speed and strength lies a sophisticated chemical reaction, where chemistry and physics work together right in the palm of your hand. Over the next few minutes, we'll uncover the 3 secrets behind its incredible strength, before discovering why this extraordinary glue also has some very clear limitations. The first secret begins with the very moment this glue revealed its true potential. In 1951, at a laboratory in Tennessee, chemist Fred Joyner placed a drop of cyanoacrylate between 2 glass prisms of a refractometer to take a measurement. When he finished, he reached over to separate them, just as he had done countless times before. But they wouldn't budge. The 2 pieces of glass had become one. So, what made the reaction happen so incredibly fast? Most glues need time. You spread them onto a surface, wait for the solvent to evaporate, and only then do they slowly harden, a process that can take hours or even an entire day. Cyanoacrylate works differently. It doesn't need to evaporate. It needs water, which sounds almost impossible. More precisely, it needs an extremely small amount of moisture, the kind that's naturally present on almost every surface, including your own skin. The moment cyanoacrylate comes into contact with that thin layer of moisture, millions of its molecules immediately begin linking together into long chains, all within a matter of seconds, before you even have time to adjust the position of the 2 surfaces. The reaction happens so quickly that the pressure from your hand is effectively locked in at the exact moment the 2 surfaces are pressed together. They are almost frozen in place. And that's exactly what happened to Fred Joyner's 2 glass prisms, all in the blink of an eye, before he even realized it. By now, you may be wondering about something. If cyanoacrylate hardens the moment it comes into contact with moisture, why doesn't it glue itself solid inside the very bottle that holds it? The answer lies in how the bottle is designed. The inside of the bottle is kept as dry and airtight as possible. At the same time, a small amount of a mildly acidic stabilizer keeps the molecules in an almost dormant state. No moisture means no reaction. That's also why the nozzle often becomes clogged after just one use. The tiny amount of glue left at the tip has already been exposed to moisture in the air and hardens before the rest of the glue inside the bottle. It's also why many people store superglue in the refrigerator together with a moisture-absorbing packet to help extend its shelf life. The real magic of superglue isn't inside the bottle. It's in the way it reacts with the world outside. But hardening quickly is only part of the story. The real strength comes from what that reaction actually creates. Imagine that each cyanoacrylate molecule starts out as a separate building block, floating freely inside the drop of liquid glue. Millions of these molecules rapidly link together into long polymer chains, which then intertwine to form one continuous network that spreads throughout the thin layer of glue and bonds to both surfaces at the same time. Superglue doesn't simply dry, it transforms into an entirely different material. A continuous molecular network that connects one surface to the other, locking them together into what is almost a single solid piece. When two surfaces are properly prepared, the part that fails is sometimes not the glue itself, but the material around it. The tensile strength of a cyanoacrylate bond can reach as high as 3,000 or even 4,000 pounds per square inch. That's why the demonstration you saw at the beginning of this video wasn't a magic trick. It was the result of millions of polymer chains working together to share the load. At this point, another question is worth asking. If the polymer network is so strong, why not use a thick layer of glue to make the bond even stronger? Why is a single thin drop enough to hold two objects together? The answer lies in the glue itself, just before it hardens. Cyanoacrylate has a very low viscosity. It's much closer to water than to honey, allowing it to spread into an extremely thin, even layer instead of forming thick puddles. More importantly, no surface is ever perfectly smooth. Wood, plastic, and metal may look flat to the naked eye, but under magnification they are covered with countless tiny grooves and microscopic valleys. Because of its low viscosity, the liquid glue flows deep into these tiny spaces through a phenomenon known as capillary action, much like water climbing up a narrow tube. This creates thousands of microscopic anchoring points that work together with the polymer network. And this is where a surprising paradox appears. Most people assume that the more glue you use, the stronger the bond will be. In reality, the opposite is often true. If the glue layer is too thick, the material deep inside may not cure evenly. Tiny voids and internal stresses can develop, weakening the bond. Only when the glue layer is thin enough can it cure evenly throughout. In other words, when it comes to superglue, less really is stronger. The three secrets we've uncovered so far might make superglue seem almost unbeatable. But the truth is a little more complicated. A cyanoacrylate bond can have a tensile strength of 3,000 or even 4,000 pounds per square inch, strong enough to hold the weight of an entire car. But that's only true when the force is applied in one direction, pulling straight apart from opposite sides. If the force comes from a different direction, such as twisting or sideways stress, the story changes completely. Under those conditions, the strength of the bond can drop to only a small fraction of its tensile strength. Why is there such a huge difference? The answer lies in the very polymer network that gives superglue its remarkable strength. Once it has fully cured, the polymer chains become extremely rigid, with very little flexibility. The same property that allows them to lock two surfaces tightly together also makes them poor at absorbing bending or twisting forces. In that sense, they behave more like glass than rubber, very hard, but also brittle. When subjected to bending or twisting, tiny cracks can spread rapidly through the material. That's why repairing a mug handle with superglue is usually not a long-term solution. Every time you pick up the mug, a small twisting force is applied to the handle, quietly weakening the bond until one day it suddenly breaks. So the strength of superglue is not absolute in every direction. It's a conditional strength, exceptionally strong in one type of loading, yet surprisingly fragile in others, And it was precisely those limits that would later be tested in some of the harshest environments imaginable. The true strength of superglue has been tested in some of the harshest environments imaginable. And one of the clearest examples came from a completely unexpected accident. In the late 1970s, at a crime laboratory in Japan, forensic fiber and hair analyst Fuseo Matsumura was using superglue to mount a sample onto a microscope slide. When he looked back, he was stunned. A fingerprint that had been completely invisible just moments before had suddenly appeared in remarkable detail, revealing even its finest ridge patterns. The vapor released by the glue had reacted with tiny traces of moisture and oils left behind by a fingertip, rebuilding the fingerprint as a thin white layer of polymer. The technique quickly spread to the United States, and to this day, it remains one of the most widely used methods for developing fingerprints at crime scenes across America. But that wasn't its only life-saving application. During the 1960s, the near-instant curing speed of cyanoacrylate was also used by U.S. military medics as an emergency way to help stop bleeding on the battlefield, sealing wounds long enough for injured soldiers to reach proper medical treatment. And for the man who made all of this possible, recognition came late, but it was well-deserved. In 2010, at more than 90 years old, Harry Coover received the National Medal of Technology and Innovation from President Barack Obama. The man who had twice dismissed a liquid as too sticky to be useful lived long enough to see it save lives, solve crimes, and become one of the most famous inventions of the 20th century. The bottle of superglue sitting quietly in your drawer has been used to lift a 150-pound man and even hold up an entire car with someone inside. Not because of magic, but because of the 3 secrets we've uncovered today. But perhaps the most remarkable part of this story isn't the glue itself. An invention that was thrown away twice by its own creator eventually went on to save lives, solve crimes, and earn one of the highest scientific honors in the United States. The line between failure and a world-changing invention is sometimes nothing more than having the patience to take one more look instead of throwing away something you don't fully understand. Who knows? Maybe somewhere in a drawer in your own home, there's a failure waiting for someone curious enough to see it differently.